So let's go ahead and get started. Just to remind you, we're talking about how to create phylogenetic trees. And the steps in this process are to decide on what sequences you're going to use, get that sequence data, do an alignment, and now what we're going to talk about today is how to use that alignment to create a phylogenetic tree. So there are lots of ways to create phylogenetic trees. Remember, remember what a tree is. A tree is just a graph. It's a graph that represents some measure of similarity amongst a collection of sequences. It's math. That's all it is. One way to do this, and one of the simplest ways, and it turns out for ribosomal RNAs, one of the best ways to do it, is a process called neighborjoining. And you've heard about this in genetics. Neighborjoining is a specific method amongst a larger collection of methods that are called least squares distance matrix methods. And so what this means is you take the alignment and you reduce the information in the alignment to a distance matrix. You have some way of for every set of sequences, every pair of sequences, estimating or calculating a number that represents how similar they are. And you throw all the rest of the information away. And you use that matrix then to generate this graph. There are other ways, and we're going to talk about those next time in brief. But this is a simple way, and it's an easy to understand way. And in fact, it's the sort of thing you can do with a calculator and pencil and paper. So you start with a sequence alignment. Here we have 6 chunks of sequences in an alignment. And to convert this to a distance matrix, there's actually 2 steps. First is you create a similarity matrix, which is, of course, related to a distance matrix, but it's not the same. And this is entirely straightforward. For every pair of sequences, A to B, A to C, A to D, A to E, A to F, B to C, etc., all through every pair of sequences, and you just count up in some way how similar they are. Now, in the simplest scenario, which we'll use here, you just compare them and you determine the fraction of identity. In this particular case, this alignment is 20 nucleotides long. Sequence A and B, 18 of those are the same, and so you have 18 out of 20 or 0.9 similarity. That's it. You can use more complicated scoring mechanisms, which we'll talk about later. But this is the simplest scenario. And you do this for every pair of sequences in the alignment, and you end up then with a similarity matrix. So again, it's a matrix, A to F, and then for every unique pair, you put in a number. You don't have to calculate the numbers on the diagonal, right? A to A is always going to be 1, B to B is always going to be 1, etc. You don't have to calculate on both sides of that diagonal, because whatever the distance from A to B is, that's going to be the same as from B to A. You don't have to calculate all these numbers twice. You can do it once, and then just fill in the number either below or above the diagonal, and you're finished. And so these numbers then, here's A and B, 0.9 similar, you put that number right here. And you do that for every pair of sequences. By the way, when doing this with a piece of paper, the most common error is that people just get off on the columns and don't put the numbers in the right places. Computers never make that mistake. Computer programmers do. So that's a similarity matrix. That's something you measure directly, right? But a similarity matrix is an underestimate of how much evolutionary distance there is between sequences. And so you have to take that similarity and approximate and estimate how much evolutionary distance that represents. So we're going to convert that similarity into a distance matrix where the numbers represent how much evolutionary distance there is between sequences. One of the best ways to do that is the Jukes and Cantor method, and this demonstrates why this is important. And so this is a curve. The equation is evolutionary distance is negative 3/4 the natural log of 1 minus 4, the inverse of similarity divided by 3. I don't expect you to remember that. But when you take observed sequence similarity, this is what's in the similarity matrix, and you graph out this equation, this is the curve you get. And so a similarity of 1, that is two sequences that are identical, has 0 evolutionary distance, right? That makes sense. And as the sequences get less and less similar, the evolutionary distance increases and approaches, but should never quite meet 25% similarity, right? Because you have A, G, C, and U, two random sequences, two sequences with infinite evolutionary distance between them, are still going to be 25% similar at random. And so this curve curves down and ultimately approaches 0.25 similarity. What this means is that the more similar two sequences are, the more distance is the inverse of similarity. But as you get further out here, you get more and more evolutionary distance. Another way to think about this is what's actually happening with the sequences. What this means is that two sequences that are 50% similar are more than 50% different. They're about 0.77. Why is this? If two sequences are 50% similar, that means every base has a 50-50 chance of being the same, right? But what if you have more than one change at that position? So what if in the evolutionary history of those sequences, a base changes, and then it changes again to something else? You'll only count that as one difference, right? But it's two changes. And the probability of multiple changes at any position increases the less similar sequences are. If they're 99% identical, what are the chances that one of those changes is two changes instead of one? What's the probability that two of the bases that are the same have changed and then changed back? Pretty small, right? But if two sequences are only 26% identical, the chances are really high. And so by only looking at sequence, are they the same or different, you undercount the amount of evolutionary distance that there is between them. And this is the curve that describes that, but this curve is an estimate, because you can never really know how many changes went between those two sequences. So, you use this equation, and you just plug every number in the similarity matrix into this equation. Or if you're doing it in a graph, if you've got 0.6% identical, you follow the line here, down here, and you look up that number. You write that in the distance matrix. And so you start with a similarity matrix, and you convert it to a distance matrix. The Juice and Cantor is a great way to do that. There are lots of other more sophisticated mechanisms for that, but this works pretty well. The next step then is to take this graph of evolutionary distances, or this table of evolutionary distances, and draw it in graph form. And the mechanism for that we use here is the least squares, or excuse me, the neighbor joining method. And this method gets its name directly from how it works. Now, in this method, the neighbor joining method, you're really separating the two different parts about building a tree. First, you solve the structure of the tree, and then you solve the lengths of all the branches. There are other mechanisms for tree building that combines those processes, but in a neighbor joining, first you solve the structure, and then you figure out the distances. And so in a neighbor joining method, you start with a completely unresolved tree. We'll talk about the parts of a tree in just a few minutes. But you have a node, and then you've got a branch that goes out to each of your sequences. So we have, in the distance matrix, we had A, B, C, D, E, F, and now we've got a completely unresolved tree, a star. Now, in our distance matrix, we look at this and say, okay, what are the two closest neighbors in this distance matrix? That is, what's the smallest evolutionary distance? That's 0.11, right? Between A and B. No other smaller numbers. This implies that those are the closest relatives in the tree. And so we join them. We pull that node out. And we say A and B are specifically related to the exclusion of all the rest. And then we recalculate the tree, or excuse me, the distance matrix, by combining A and B. And so now this table, this reduced matrix represents the average distance between C and A and C and B. Between D and A and D and B. And so forth down the line. Now in this particular example, those are all the same, right? 0.38, 0.30, 1.21, 1.0. So this is trivial, because the average of 0.3 and 0.3 is 0.3. But that's not usually the case. That actually tells you something that gives you a hint about how the rest of the tree process will work. Because if the distance from any other point in the tree to A and B is the same, that means that these two branches have to be the same length, don't they? That's the key to solving the lengths of all these branches, is determining the relative lengths of the two branches in the tree. Anyway, you reduce this matrix, and now you look at it again and say, now who are the closest neighbors in this tree? And so when I look at this, the smallest number I see is C to D, 0.17. And now I join those two branches, C and D. And I reduce the matrix again. Now we have not just A and B combined, but C and D combined. And I've got the average from F to A and B, F to C and D, C to A, C to B, D to A, and D to B. All four numbers combined and averaged. And I've got another matrix. And I look at that and I say, who are the nearest neighbors in the matrix now? And it looks to me like it's E and F, 0.30. And so I pull those branches out. And I've got a tree that looks like this. This is the new node. At this point, I'm done. How do I know I'm done? Because every node has 3 branches that come off of it. I can't pull any other nodes out of there. Because if I do, the node will only have 2 branches. I suppose I have any markers. A node with 2 branches isn't a node at all, right? This is what a node with 2 branches looks like. And that's meaningless. That doesn't help at all. So I know the structure of my tree now. That part of the process is complete. So the next task is to determine the lengths of all the branches. And now I'm going to pull out of the lecture notes because this is actually one of the hard ones. Because the branch lengths don't all come out exactly even, and so you have to do a bunch of averaging. I'm going to shift to one of the problem sets. Where is it? Right here. So I've got a distance matrix right here. A to B, where is it? Problem 4 of the problem sets. I've got a distance matrix, and I've done the same process here and pulled out all the branches. The structure of the tree is the same. That's by coincidence. And so now the question is, how do I determine the lengths of the branches? You have to determine branch lengths 1 or 2 at a time. You can't solve it all directly, and it's a little bit of a puzzle. Well, I already gave you clue number 1. Oh, the other thing is that it's usually easiest to determine the terminal branches, the tip branches first, and then work your way deeper into the tree. So, if the length of the distance of any place in the tree to A and B is the same, that means that those terminal branches between A and B have to be the same length. Now we know the total length, right? The distance from A to B is 0.2. So the length of this branch and this branch together totals 0.2. And so how can you divide 0.2 into two numbers that are both the same? It's just divided by 2, right? So we know that each one of these branches is 0.1. And so you draw that on the tree. 0.1 and 0.1. Now I'm going to do, if you do these ones, E and F, the distance between E and F is 0.3. If you go back to that table, you'll see that the evolutionary distance between E and F is 0.3. But it's always 0.1 longer to E than it is to F. Let me go back and show that. From A, it's 0.1 longer to E than F. To B, it's 0.1 longer to E and F. And so what that means is the branch, that terminal branch to E, is 0.1 longer than the one to F. And the total length is 0.3. That means it has to be 0.1 to F and 0.2 to E. And so I draw that in. So. And I do the same thing to C to D. In this case, it's 0.1 longer to C than to D, and it's 0.5 total, and so it's 0.3 to C and 0.2 to D. Okay, those are the easy ones. Now the question is, how do I determine the length of these branches in the middle? So the distance from A to F in the original matrix is 0.6. I know this distance, that's 0.1. And I know this distance, that's also 0.1. And so the distance from here to here is 0.4. With B and C, if you do the same math, take the total distance and subtract these two, it's 0.3. And from D to E, it's also 0.3. And so now you can ignore these branches out here. You have another one of these three-sided triangles. Three-sided triangles, right? What other triangle are there? And you know the lengths, the relative lengths across each of the angles. And so it's 0.1 longer to A and B than it is to C and D. And so it's 0.2 and 0.1. And the number left over is 0.2 because if you add this, if you take the total length, subtract this, this, and this, 0.2 is left over. Yeah? Okay. So, you know it's 0.3 from here to here. You know the distance, for example, from A to D and from A to E, and you just subtract, you know that it's longer in that direction. It's longer in the direction to A and B than it is to C and D. So, let's see. So likewise, the internal branch between these points. Yeah. So again, you've got a three-sided triangle, just like the other ones I showed you, where the distance across that branch is longer than the others. That's it. Now, in a real tree, those numbers are never going to be even, right? And so you've got to take averages across all the paths through the tree. I'm not going to get into that. Some of the examples in this problem set do that in great detail. Here's one that goes through on and on and on. This is the kind of math that computers are really good at and people are really bad at. The point is that this is nothing but a mathematical transformation. It's arithmetic. These trees are nothing magic. Let's see. And when you're done, once you've solved the length of all the branches, it's always a good exercise to take that original structure of the tree and draw it with a scale bar and make the branches all the right length to show you what the tree really looks like. And now, when you do this, you ought to take this scale bar and be able to measure along these branches and say from A to B, you measure that, and it ought to be a pretty close match to what's in the distance matrix, right? There are a couple of caveats to this, or some interesting issues. For every tree you generate, you should include an outgroup. So what's an outgroup? An outgroup is a way to root the tree. This is an unrooted tree up here, right? It's just a splayed out diagram. But usually you want to know, in terms of evolutionary history, where organisms come from. And so you need to include a root. Well, what is a root? And this one, I'm guessing that the E and F here represent the root, and you're interested in these organisms. An outgroup is a group of organisms or sequences that you have other reason to know aren't members of the group you're interested in. And so, for example, if you're interested in the evolution of great apes, you might include an old world monkey as an outgroup, because you know that's not a member of the apes, and it allows you then, where it falls in the tree, allows you to determine the common ancestor of the organisms you are interested in this case, the great apes. If you're interested in an evolutionary tree of the bacteria in general, you might include a eukaryote as an outgroup, because that allows those eukaryotes would allow you to place the root of the bacteria, and so forth. Be very careful about your choice of an outgroup. It's important for an outgroup that it be clearly outside of the group, but it turns out for technical reasons that the closer to the group it is, the better that root will be when you're done. And so, for example, if you're interested in the great apes, E. coli is not the best outgroup to use. You want something that's a close relative, but outside the group. Right. The issue is that if your outgroup is too distantly related, the sequences are essentially random, and the evolutionary distance is a lot of guesswork. The estimate is pretty rough, and you end up with answers that are equivalent to a midpoint, a root. That is, if you wanted to root this group, you wouldn't take something really, really distantly related, because it will put the root right here regardless. It takes the longest distance in the tree, and it'll put the root more or less in here, even if that's not true, because of the way the math works out. Now this creates an interesting quandary. If you're going to do a tree, and you're going to determine where the root of that tree is, you need to have an outgroup. So in a couple days, we'll talk about how you root a universal tree. If you've got bacteria, archaea, and eukaryotes in it, how do you root that tree? You need an outgroup, right? No. Jesse Sherman. Yeah, so steel bicycle frames, which I used to be a cyclist. I've had some pretty weird notifications show up in classes, by the way. The other thing is that, so the final step is you've got a tree, you've got all the branches on there, you know how long they are, you've got an outgroup. The final step is this giant leap of faith that tree represents the evolutionary history of the organism. Because what this tree really is, which I've pounded home to you guys, is a graph representing sequence divergence. That's all. What you'd like it to be, and what you're usually seeking, is for that graph to be an evolutionary tree of the organisms you're interested in. There's a variety of reasons why this can go wrong. Number one, horizontal transfer, right? Suppose this is a tree showing ampicillin resistance genes, beta-lactamase genes in bacteria. This could be an absolutely correct graph showing the relationship between those genes, but it will not be a representation of the evolution of the organisms that you took those genes out of, because the genes have moved and evolved independently to some extent of the organisms they came from. What if these are ribosomal RNAs from plants? The first thing I'm going to think of is that one of these groups is mitochondrial and the other one is nuclear, or chloroplast and nuclear. You've got a gene family, right? You've got more than one kind of gene for the same thing in that organism. Gene families create nightmares for this. Maybe these are globins, and these are alpha globins, and these are beta globins. And that will obscure what you think is going on in the tree. There are a number of reasons, when you look at one of these things, there are a number of red flags you ought to look for. One of them is if you do another tree and you pull out one of these sequences, you ought to get a tree that looks like this, right? If you take FOE away, you ought to get a tree that looks like this. If you get a tree that looks completely different, you know there's a problem. The tree is sensitive to the inclusion of sequences, specific sequences. This is a red flag. You have large evolutionary distance between two organisms. There's two reasons why that's a red flag. One, the first thing you think of is, I don't know that these sequences are aligned very well, because if the alignment's bad, the trees will be bad. The other thing is that when you've got large differences in evolutionary length, nearly all tree algorithms have trouble estimating evolutionary distance correctly. I'm going to show you, this is called long branch attraction, and I'll show you an example of that probably next time. So take a look at this tree. Identify the organisms that you're looking at, and ask yourself, does this look right? If it doesn't look right, it probably isn't right. And think about your alignment. Think about the sequences you're using. Maybe do some experiments with adding and removing sequences to see what happens, to make sure there isn't an obvious problem going on. Okay.